To help us solve more complicated circuits, we have two laws developed by Gustav Kirchhoff, who's a German physicist who developed these laws when he was still a university student. So just keep that in mind, the clock's ticking on you guys. So anyway, the two laws help us to develop systems of equations that we can use to solve for the missing currents and the missing resistances in circuits. And so those two laws are as follows. There's the voltage law, which says that if you go around a closed loop in a circuit, that all of the voltage changes, whether they are step-ups or step-downs, ultimately have to add up to equal zero. And so if we think of a simple circuit that has just a battery and then maybe a resistor here and then a second resistor, it should make sense that if I go all the way around the loop from here and then come back, that the voltage potential that I started at needs to end up being the same. And so the voltage drop that we have across this resistor or this resistor added to the voltage step up that happens at the battery, all of those have to cancel each other out to equal zero. That's basically what the voltage law means. Is if you take any closed loop in a circuit, even if there are more, let's say, loops added onto it, then any individual loop that you take, the voltage changes around that loop are going to add up to equal zero. And then the second law that we have is Kirchhoff's current law, which basically says whenever you have a junction, so let's say it's this point right here, whatever current is flowing into that node has to equal the current that's flowing out of the node. So the net current at any one location is going to end up equaling zero. So all the inflowing currents, let's say we had current flowing in from both of those directions, that would have to equal what's flowing out of that junction going the other way. And so taken together, we can use these equations to help us build a system of equations to solve for the missing elements, missing currents, missing resistances, whatever it might be, in a more complicated circuit than just a single battery or a single loop. So in the example we have here, we have a couple of batteries. We have a 10-volt battery here on the left, the positive terminal here and the negative below. And then we have a 20-volt battery on the other side, again, positive terminal here, negative below. And then we have these two loops joined together where we've got a resistor 1 at the top here that's 10 ohms, a resistor 2 that's 20 ohms, and then the resistor in the middle of the circuit is a 40 ohm resistor. And so what we want to figure out is what is the current that is flowing through that third resistor, the one that's in the middle. Ultimately, we're going to need to figure out what these currents are as well, flowing through 1 and 2, but our only ask here is what's flowing across that third resistor. Now, for this, we're going to need to set up a system of equations. There's essentially three variables that we have to solve for. There's the three currents. And so in order to solve a system that has three variables, we're going to need a system of three equations. So I'm going to start off and I'm going to use this node A and use Kirchhoff's current law to write an equation. So that's going to be my first equation. And that's generally a good place to start. Those are kind of the easiest equations to piece together, the ones where you just have a junction of wires and different currents flowing in and flowing out. Now, we can choose, similar to what we did back with our trusses that we studied, we could choose to try to guess which direction the current is flowing, or we could be arbitrary about it and just say it's always going to go clockwise or it's always going to go counterclockwise or whatever. And if we happen to be wrong, it just means that our current answer will end up being negative. So ultimately, it doesn't really matter that you're correct in your guess as to which direction you think the current is going to be flowing through a given resistor or around the circuit, but you just need to make sure that you realize that you assigned it a direction for the purposes of building your equation, and then therefore whatever your positive or negative answer is determines whether or not your indicated guess was right or not. So for our purposes, we're going to go with the arrows that we see here. We're going to assume that the current in the left-hand side is going through resistor 1, I1 is flowing to the right, and then current I3 is flowing down. And then similarly here in this loop here, we're going to guess that based on how the batteries are positioned, this makes the most sense, that current 2 through resistor 2 is flowing to the left, and then again down through R3. We may be wrong. It may turn out that this is not correct. That will just show up with negative signs for our answers when we eventually solve our system of equations. But again, going back to node A here, based on the way we've got the currents described, going into the node, we have current I1 and we have current I2. As diagrammed, both of those are flowing into node A, into that junction, and then that's going to equal what's flowing out of the junction, and so that's current 3, as we can see in the middle of the diagram right here. So I1 plus I2, the current that's flowing into the junction, has to equal the current that's flowing out according to Kirchhoff's current law. So that's our first equation. So I've cleaned up our diagram a little bit because now we're going to have to use Kirchhoff's voltage law with a couple of closed loops around our circuit in order to generate 2 more equations to then have a system that we can solve. So I'm going to start off with the loop that's over here on the left-hand side. So loop 1, we'll refer to it. And I'm going to start at this point right here, point C. And so as I go around the loop, I'm going to I'm going to put all of the current and resistor voltage drops on one side of the equation, and then I'm going to put the batteries, the step-ups in voltage, on the other side. So as we go around, we've got I1 times R1. So as we work our way around the loop, so we've got current 1 flowing through resistor 1. Now we know what resistor 1 is, it's 10 ohms. So I'll fill that in just a second, but I just want to leave it like this first. So we've got that first voltage drop. So as we move through that resistor, the voltage drops. Then we continue through node A. There's no voltage change after we've gone through that resistor until we now hit resistor 3. And so when we hit resistor 3, we have another drop. So I'm adding together my voltage drops on one side, and I'm going to put the batteries on the other. So on the other side here, or through this one here, we've got I3 times R3. And again, we know that resistor 3 is 40 ohms. We'll fill that in just a second, but I just want to leave it in this Ohm's law format. And then finally, we continue around this loop, and then the last thing we do is we go through this battery, and we're going through this battery the correct direction from the low potential to the high potential side. So that means we have a step up in voltage of 10 volts. So these 2 voltage drops, I1 R1 and I3 R3, have to add together to equal the voltage step up that we have on the other side. So I'm going to clean these up now since R1 is 10. So I have 10 I1 plus 40 I3 equals 10. So there's our second equation. We've got our first one right here from Kirchhoff's current law. We've got our second one here from Kirchhoff's voltage law applied to that left-hand loop. And so now I'm going to do the same thing over here on this right-hand side, starting from point D, working my way around this loop 2. So the first thing we have is we have a voltage drop across that resistor. So using Ohm's law, we've got I2 times R2 plus, now we continue, we go down through node A, and so our next voltage drop is again through this resistor 3. So we've got I3 times R3, and then we keep on going around this loop, and so then the last object we hit is this battery, and we are again going from the low potential side to the high potential side, and so we have a step up of 20 volts, so that's going to go on the other side of our equation. So now if we plug in those resistance values, I2 is 20, so we've got 20, or R2 is 20, 20 I2 plus again 40 I3 equals this 20 volts. So now we have our system of 3 equations and 3 variables. The first one from Kirchhoff's current law applied to node A, and then the other 2 from the closed loops using the voltage law. And so now we just need to solve this system of equations. And so in this first equation, I've got I3 already isolated. And so we know that that equals I1 plus I2. So I'm going to make that substitution into equation 2 and into equation 3 right here. So I'm moving from a system of 3 equations and 3 variables down to 2 equations and 2. So I'm just using my solving techniques from math classes in our past. So the equation 2 is going to become 10I1 plus 40 times I1 plus I2 equals 10. And then the second equation is going to be 20I2 plus, again, same thing, 40 I1 plus I2 equals 20. And so if we distribute and gather like terms, 10I plus this 40I is going to give me 50I1 plus 40I2 equals 10. And then doing the same thing here, I've got 40I1 plus 20I2 plus another 40I2 after I distribute makes 60I2 equals 20. And so now we're getting a little bit closer. I'm going to choose to go ahead and eliminate the i's. So I'm going to multiply this equation here by 4 and then this bottom equation here by 5. So I end up with 200 I1 plus 160 I2 equals 40. And then for the second equation, I get 200 I1 plus 300 I2 equals 200. And so, or sorry, 100. My apologies there. And so then I'm going to subtract these equations to get the i's to disappear, but I'm going to subtract the bottom one minus the top just so I end up with positives. I'm an optimistic guy. So those go. 300 minus 160 gives me 140 I2 equals 100 minus 40 is 60. So then if we divide both sides by 140, we'll get the current I2 is equal to 0.43 amps if we round off to 2 significant figures, which is what we should be carrying throughout here. So what that confirms for us is that our guess that the current I2 was flowing from right to left is indeed correct because we got a positive answer. And so now I can go through and I can back substitute. I can take I2 and say plug it in either here, or maybe in one of these cleaner versions here or here to figure out what I1 is. And so if we plug that in, we find negative 0.14 amps is our current I1. So getting a negative answer tells us that in fact the current is flowing also in this resistor from right to left. Now this seems strange since we have a battery that's driving potential this direction, so this implies that the current is flowing backwards through this battery, but what's happening here is this battery here that's 20 volts is overwhelming the 10 volt battery on the other side, and so that's driving the current back into that other direction. And so finally, since we have in equation 1 right here, I1 plus I2 equals I3, we can find what we were after, the current that's flowing through resistor 3. And so if we add 0.43 and negative 0.14, we get 0.29 amps. So the current is indeed flowing down through that resistor in the circuit as we guessed at the beginning. So it's just our I1 current that is the opposite direction of what our initial positive and negative, or our initial guess was based on the negative sign. And then if we want to figure out what the voltage across R3 is, now we know the resistance is 40 ohms, that was given. We now know the current, and so the voltage drop across that resistor, if we multiply 40 times 0.29 and round off to 2 significant figures, we'll get a drop of 11 volts. So this is how we can take a complicated circuit with multiple batteries, multiple loops, multiple resistors, and set up a system of equations to allow us to solve for the currents and then eventually the voltage as required.